Hello great minds! Welcome to Scholar's Edge tutorial. In this video we would be looking at the subject, physics. Topic, elasticity. What is elasticity? Elasticity is the ability of a deformed material body to return to its original shape and size when the forces causing the deformation are removed. It describes the material's capacity to deform under load and then recover its original form when the load is removed. What are the types of elasticity we have? Let's find out. 1. We have linear elasticity. In linear elasticity, the material returns to its original shape and size in proportion to the applied force. Imagine you have a rubber band. When you stretch it, it gets longer, right? Now, if you let go of it, it returns to its original shape and size. That's linear elasticity. It means that when you apply a force like stretching to an object, it will 1. Deform, which is to get longer or change shape. 2. Return to its original shape and size when the force is removed. The key point is that the object returns to its original state in a straight line, without any permanent change. It's just like the rubber band snapping back into place. In linear elasticity, the more force you apply, the more the object deforms. The deformation is directly proportional to the force applied. When the force is removed, the object returns to its original shape and size. Using a spring as an example, you compress or stretch it, and it returns to its original shape when you let go. That's linear elasticity. Next we have is non-linear elasticity. In non-linear elasticity, the material's deformation is not directly proportional to the applied force. Imagine you have a plastic ruler. If you bend it slightly, it will return to its original shape when you let go, but if you bend it too much, it will start to deform permanently and won't return to its original shape. In non-linear elasticity, the object deforms but not in a straight line. The deformation is not directly proportional to the force applied. The object may not return to its original shape and size when the force is removed. Using a piece of chewing gum as an example. When you stretch it a little, it returns to its original shape, but when you stretch it too much, it loses its shape and doesn't go back to its original form. That's how non-linear elasticity behaves. The object response to force is not predictable or directly proportional, and it may undergo permanent changes. Examples of non-linear elasticity includes 1. Plastic deformation, like bending a paperclip. 2. Fracture, like breaking a glass. 3. Creep. Like a piece of clay slowly deforming under constant pressure. In summary, linear elasticity is like a rubber band or spring where the object returns to its original shape, while non-linear elasticity is like a plastic ruler or chewing gum where the object deforms permanently or loses its shape. Next on the types of elasticity, we have Hooke's law. Hooke's law is a simple concept that describes how materials behave when they are stretched or compressed. It's named after Robert Hooke, who discovered it in the 17th century. Hooke's law states, the force required to stretch or compress a material is directly proportional to the distance of stretching or compressing. In simple terms, if you stretch a material a little, it will take a small force. If you stretch it a lot, it will take a bigger force. The more you stretch, the more force is required. Using a spring as an example. When you pull a spring a little, it takes a small force. When you pull it a lot, it takes a bigger force. The more you pull, the harder it gets. Hooke's law only applies to materials that behave elastically, meaning they return to their original shape when the force is removed. It's a linear relationship, meaning the force and distance are directly proportional. The law is often represented by the equation F equals kx, where F is the force applied. K is the spring constant, a measure of the spring stiffness. X is the distance of stretching or compressing. That's all for the types of elasticity. Now we move over to key concepts in elasticity. 1. Stress. Stress is a measure of the force applied to an object, divided by the area over which the force is applied. Think of it like this. Imagine you are pushing on a wall with your hand. The force you're applying is spread out over the area of your hand. If you focus that same force onto a smaller area, like your finger, the pressure increases. Stress is calculated as stress equals force divided by area. The unit of stress is typically measured in pascals or pounds per square inch. Here's an example. If you apply a force of 100 Newton to an area of 10 meter per second, the stress is 10 pascals. If you apply the same force to an area of 1 meter per second, the stress increases to 100 pascals. Stress can be thought of as the pressure on an object. When an object is subjected to stress, it can deform or even break. There are different types of stress, which includes tensile stress / pulling apart, compressive stress / pushing together, shear stress / sliding force. Stress is a key concept in elasticity because it helps understand how materials behave when they're subjected to forces. Next is strain. Strain is like stretching. Imagine you are stretching a rubber band. When you stretch it a little, it gets a little bit longer. When you stretch it more, it gets even longer. Strain measures how much an object changes shape when it's subjected to stress. Think of strain this way. Strain is the stretch or deformation of an object. The more stress an object experiences, the more strain it undergoes. Strain is usually measured as a percentage or a decimal value, like 0.05 or 5% of strain means the object has stretched by 5% of its original length. There are two main types of strain, which are tensile strain or stretching, compressive strain or compressing. Here's a simple example. Imagine a metal wire with a length of 100 centimeters. When you stretch it by 5 centimeters, the strain is 0.05 or 5%. If it returns to its original length when you release the force, it's elastic. Next we have is elastic limit. Elastic limit is the maximum stress an object can withstand without permanently changing shape. Using a rubber band as an example. When you stretch it within its elastic limit, it returns to its original shape. But when you stretch it beyond its elastic limit, it deforms permanently and won't go back to its original shape. In other words, the elastic limit is the point of no return. If you stay within the elastic limit, the object will deform temporarily, return to its original shape when the force is removed. But you exceed the elastic limit, the object will deform permanently, not return to its original shape when the force is removed. The elastic limit is important because it helps us understand how much stress an object can handle before it's damaged or deformed permanently. Here's a simple example. Imagine a metal wire with an elastic limit of 500 Newton. If you apply a force of 400 Newton, it will deform temporarily and return to its original shape. But if you apply a force of 600 Newton, it will deform permanently and won't go back to its original shape. Next is proportional limit. Proportional limit is like a boundary beyond which an object starts to behave strangely. Imagine you are stretching a rubber band. At first, the more you stretch, the more force it takes. This is like the proportional limit. But if you keep stretching, it gets to a point where it starts to stretch more easily. This is beyond the proportional limit. Within the proportional limit, the rubber band stretches in a predictable way. The more you stretch, the more force it takes, directly proportional. Beyond the proportional limit, the rubber band starts to stretch in an unpredictable way. It might even break or deform permanently. Think of it like a speed limit. Within the speed limit, you can drive safely and predictably. But if you exceed the speed limit, you risk losing control or getting into an accident. The proportional limit helps us understand when an object is likely to behave or get damaged. Lastly, we have modulus of elasticity, Young modulus. Modulus of elasticity is like a measure of how flexible or stiff an object is. Imagine you're holding a spring. If it's easy to stretch and flexible, it has a low modulus of elasticity. If it's hard to stretch and stiff, it has a high modulus of elasticity. Using a ruler as an example. A flexible ruler has a low modulus of elasticity. A stuff ruler has a high modulus of elasticity. The modulus of elasticity, also called Young modulus, measures how much stress it takes to cause a certain amount of strain in an object. In simple terms, modulus of elasticity equals stress divided by strain. A high modulus of elasticity means an object is stiffer, less flexible, and more resistant to deformation. A low modulus of elasticity means an object is more flexible, less stiff, and more prone to deformation. With the knowledge we've gotten on elasticity, let's solve some questions. 1. The elastic limit of a material is the A. Maximum stress it can withstand. B. Minimum stress it can withstand. C. Stress at which it begins to deform plastically. D. Stress at which it breaks. The correct answer for question 1 is option A, maximum stress it can withstand. Remember that the elastic limit is the maximum stress an object can withstand without permanently deforming. Number 2 question. A force of 100 Newton is applied to a wire of length 50 meters and cross-sectional area 0.01 meter. If the wire stretches by 0.1 meters, calculate the modulus of elasticity. When solving questions like this, the first thing you need to do is to write out your parameters. So from the question we were given force as 100 Newton, length as 50 meters, area as 0.01 meters, extension as 0.1 meters, and we were asked to find elasticity. Recall that the formula for elasticity is E equals stress divided by strain. And we were not given stress nor strain, so let's find our stress and strain first. Formula for stress equals force divided by area, which is equal to 100 divided by 0.01, giving us 10,000 Newton per meter square. Solving for strain. Strain equals extension divided by original length, which is 0.1 divided by 50, giving us 0.002. Strain doesn't have any unit, reason because extension is in meters and length is in meters, and if you divide the 2 meters, you would be left with nothing. Now we've known our stress and strain, substitute it into elasticity equals stress divided by strain, which is 10,000 divided by 0.002, giving us 5 million Newton per meter square, or 0.005 gigapascal. Number 3. Which of the following statements is true about elasticity? A. Is the ability of a material to deform permanently. B. It is the ability of a material to return to its original shape after deformation. C. It is the ability of a material to conduct heat. D. It is the ability of a material to conduct electricity. The answer is option B. It is the ability of a material to return to its original shape after deformation. Recall that elasticity is the ability of an object to return to its original shape after the applied force has been removed. Question number 4. A metal wire of length 2 meters and cross-sectional area 0.02 meters is stretched by a force of 50 Newton. If the extension is 0.02 meters, calculate the stress and strain. So listing out our parameters. Length equals 2 meters. Area equals 0.02 meters. Force equals 50 Newton. Extension equals 0.02 meters. And we're asked to find stress and strain. Solving for stress. Stress equals force divided by area, which is 50 divided by 0.02, giving us 2,500 Newton per meter square. For strain, we have strain equals extension divided by original length, which is 0.02 divided by 2 is equal to 0.01. Moving over to question number 5. What is the unit of modulus of elasticity? A. Newton per meter square. B. Newton per meter. C. Pascals. D. Joules per meter cube. The correct answer is option C, pascals. The unit of modulus of elasticity is indeed pascals, which is equivalent to Newton per meter square. Question number 6. In a hydraulic press, the pump piston exerts a pressure of 100 pascals on the liquid. What force is exerted in the second piston of cross-sectional area 3 meters square? Listing out our parameters. Pressure, which is same as stress, equals 100 pascals. Area equals 3 meters square, and we are asked to find force. Recall that stress equals force divided by area. Making force the subject of the formula, we cross-multiply. Force equals stress times area, which is 100 times 3 equals 300 Newton. Question number 7. If a wire 30 centimeters long is extended to 30.5 centimeters by a force of 300 Newton. Find the strain energy of the wire. A. 7.50 joules. B. 750 joules. C. 75 joules. D. 0.75 joules. So let's list our parameters. Length equals 30 centimeters. Extension equals new length minus old length, which is 30.5 minus 30 equals 0.5 centimeters. Converting to meters, we have 0.005 meters. Force equals 300 Newton. Formula for energy or strain energy is half times force times extension. Substituting our parameters into the formula, we have half times 300 Newton times 0.005 meters equals 0.75, and the unit of energy is joule, so we have 0.75 joule, making option D the correct answer. Question number 8. Calculate the energy stored in a stretched spring of spring constant 1.0 by 10 raised to the power of 4 Newton per meter, when a force of 200 Newton is applied to its end. A. 2000 joules. B. 200 joules. C. 0.2 joules. D. 20 joules. Listing out our parameters, we have spring constant K is equal to 1.0 times 10 raised to the power of 4 Newton per meter, which when converted to standard form, we have 10,000 Newton per meter. Force equals 200 Newton. And we are asked to find energy. Recall that formula for energy is half times force times extension, but we weren't given extension. In order to look for extension, we use the formula, force equals constant times extension. Making extension the subject of the formula, we have force divided by constant, which is 200 divided by 10,000 is equal to 0.02 meters. Now we have our extension, let's substitute into the formula for energy. Energy equals half times force times extension. Energy equals 1/2 by 200 by 0.02, giving us 2 joules. Last but not the least, question 9. A spring of length 5 centimeters is extended by 0.04 meters, when a load of 0.8 kilogram is suspended at the end. How far will it extend if a force of 16 Newton is applied? Acceleration due to gravity equals 10 meter per second square. Listing out our parameters, we have length equals 5 centimeters. Extension 1 equals 0.04 meters. Force 1 equals 0.8 kilogram, converting to Newton, we multiply it by the acceleration due to gravity, which is 0.8 times 10 is equal to 8 Newton. Force 2 equals 16 Newton. And we are asked to find the second extension. In questions like this, the first thing we need to do is find the spring constant K. So we go like this. Force 1 equals constant times extension 1. 8 equals constant times 0.04. Making K the subject of the formula, we have K equals 8 divided by 0.04, giving us 200 Newton per meter. Now we've gotten the constant, let's find the second extension. Force 2 equals constant times extension 2. 16 is equal to 200 times extension 2. Making extension to the subject of the formula, we have extension 2 equals 16 divided by 200, giving us 0.08 m. So our second extension is 0.08 meters. That's all on elasticity. We hope we've been able to impact knowledge and given you a deeper understanding on the concept elasticity. Thanks for watching. Don't forget to subscribe, like and share. If you have any question, drop on the comment section, and we will make sure we answer you. Stay tuned for our next video. Bye.